represent, these glaciers do represent important components of the hydrosystems, and people rely on the water flow for nourishment in agriculture. Okay, so when we talk about the term cryosphere, and again, I can't see show of hands, but I suspect that several of you are high school students that teach the physical sciences. Perhaps there's some social science teachers out there too, and a combination of both. The cryosphere is a term we use to collectively refer to all forms of frozen water on Earth's surface. So that water is primarily stored in the great ice sheets, so Antarctica and Greenland ice sheet. We have smaller components of frozen water that represent sea ice, an important component of the climate system, of course, in northern environments. And then we also have mountain glaciers, ice caps. And this is really kind of where I've focused my research in the last several decades. And this particular graph is a trace of annual temperatures up till about the year 2020 from the Goddard Institute of Space Studies. This is from NASA's, one of NASA's research institutes that compiles all of the surface observations of temperature for the planet. And what's clear is that, at least for the last 125 years, Earth's temperature, when you take all of those station records together, you average it, it has been getting warmer. We had a warming in the early 1940s, but this warming really didn't take off until about the late 1970s, and it is more or less continued unabated. And this has been shown through numerous studies to be caused in large part by humans and the introduction of greenhouse gases. This green trace is actually the average of 38 climate models that were represented and reported out in the last Intergovernmental Panel of Climate Change. What's clear is that when you take the average of all of these models under a high emission scenario, that's what that SSP 585 represents, it's not going to get the year-to-year variation, but it gets the average and the decadal average quite well. So this is an important point, that these models are not and have never been developed to say something about the year-to-year variability, but rather the long-term trends. And so when we think about how those models are going to project what's going to happen in the future, this suite of experiments is the high emission scenario. So if we continue to introduce greenhouse gases to the atmosphere with no mitigation, this is kind of the sad story towards the end of the 21st century, is that we're really looking at about 5 degrees of warming on average for the planet. So when you look at sort of high latitudes, such as the Arctic, we're looking at something like perhaps almost 8 degrees. So this is the global average. But the point of this graph is just to show these climate models are relatively good at sort of forecasting what has happened in the last 100 years. And they also are good tools to say something about the future in terms of the thermal change. Okay, I'm going to bring it back a little bit closer from the globe back to Western Canada. That's where I do most of my work. And just to give you an idea, I too am speaking from the traditional land of the Lheidli-T'enneh. And so that is sort of right at where my cursor is here. This is about where Prince George is. Most of our ice in Western Canada exists in the Coast Mountains, here close to the Pacific Ocean, and also in the interior and Rocky Mountains. And if you haven't been to Prince George, this is a high elevation plateau. This is on which Prince George sits. In British Columbia, we get about 90% of our electricity from surface runoff. And by and large, that most of that electricity, or practically all of it, is indeed from hydropower generation. We also have transboundary water, so water from the Columbia Basin that flows down into the US and then out in Portland. Also along the Alaska borders here, we have water from both snow and ice that transcends or goes into other countries, namely the US. So transboundary water is an important component, not just here, but in other places of the planet where water becomes somewhat of a conflict in terms of how much and when is it delivered. These glaciers typically melt in late summer, so they provide important flow regulators and thermostats to many of these headwater streams when seasonal snow has been depleted. And the final point is these glaciers are really interesting because they are controlled and conditioned by variations in climate. In the present day and in the projected future, they're not expected to fare well, but in times of the past, when humans had not modified the landscape and the climate system, we find that these glaciers were finely tuned to variation in past climate. So we can examine their deposits and variations to say something about past climate variability. It's not something I'll talk about today, but it is something that my research group has done in the past. This is an example of a small glacier in the northern Yukon. We were up here last summer in the easternmost portion of Yukon. This is called the Itzy Glacier. And you can see lying down valley from the glacier at the top here, these prominent deposits of rock and debris. These are called end moraines. So they demarcate a time that the glacier was much more extensive. I have a student looking at this. We think it's about 300 to 400 years ago before present. But you can envision that these glaciers are sensitive to climate. If it gets cooler or wetter, they undergo expansion. And if it gets warmer and drier, they can, in concert, shrink and reduce their volume. And so I put this in just to remind you that we're going to talk mostly about observations in present day, but we can look at these observations in the past as well. I was coming back. I was fortunate enough to have spent a month in France the last month as part of a sabbatical visit in Toulouse. And when people asked me how it was, I said it was horrible. 2 hours of walking to a research institute every day, enjoying good French wine. It was horrible. I'd never do it again. But of course, I'm teasing. It was a great time. On the way back, I was fortunate enough to get a window seat and sort of witness the eastern portion of the Greenland ice sheet. The trajectory of the plane goes right over that. A little bit of an irony, of course, I'm on this carbon belching aircraft and then witnessing the beauty of this landscape below me. But just to give you a perspective, when we talk about Western Canadian glaciers, if we melted them overnight, which is impossible to do, but by the end of the century, highly likely, we're talking on the order of about 1 millimeter of sea level rise. Not a lot. So it's not a sea level rise story. It's really a water resource and timing availability story for Western Canada. The Greenland ice sheet, on the other hand, you melt this overnight, or it's rather think about the sea level rise potential. We're talking 7 meters, and that is not out of the cards for the next several hundred years. So society really needs to get its act together in terms of dealing with our dependency on fossil fuels and how we are to adapt to some of the inevitable changes that lie ahead. Okay, let's consider a small headwater stream in Western Canada or any glaciarized watershed. And you can envision the hydrographs. So this is a little cartoon showing just take runoff as the amount of water going through a river per unit time. If we wanted to get technical, we could call it discharge. And then we could look at the corresponding time that discharge or runoff is released to a watershed. For a typical unregulated watershed, that is with no dams, no reservoirs, This is a typical hydrograph that we might expect in the during snowmelt and then later glacier runoff. When we regulate those flows, that is, we put in some sort of containment structure to alleviate flooding or to alter the timing of flooding, we find that the base flows, the low flows, tend to go up, the peak flows go down for flood control management. And overall, we start to modify this hydrograph for good or bad. Won't really talk about regulated flow today. But when we talk about glaciers, we're really talking about this component of the hydrograph that I've colored here in green. This is where the seasonal snow has melted away, and this fraction or this volume of water is that which is produced by the glaciers. Now, if the glaciers were in climatic equilibrium with present day climate, that is, they're not growing, they're not shrinking, we would still expect to find runoff entering those river systems. It's rather when those particular glaciers are in an imbalance with present day climate, such as what we have here, where they're losing more volume than they're gaining, we actually get a surplus of water. And that's what people have referred to as a glacier dividend excess. Think of it as the interest paid on a bank account on top of the principal. Well, of course, this is a fool's errand to think that this is going to continue, because this is the fraction of the glacier which will eventually no longer be there. So in a warming climate, the glacier is getting smaller. It's also thinning. And so we're having less runoff generated over that surface. So that does not last. And what we get is we get a removal of this part of the hydrograph. In terms of total volume, it's not a lot, but it is heavily sensitive, or that is, it's quite important to aquatic ecosystems, this fraction during late summer when seasonal snowpack has been depleted. Okay, so how do we observe glaciers and glacier change? Well, some of the earliest ways, of course, Western Canada is not unique to this, but we also have this in different parts of the world. We have repeat photographs. This is a photograph taken by one of our earliest surveyors, A.O. Wheeler, that was surveying for the Canadian Rails system. This was in Glacier National Park. So this is Illecillewaet Glacier at about 1910. And then this is the corresponding glacier as it existed in 2011, taken by the Mountain Legacy Project. So you can see that glacier has undergone lots of change, not surprising. So that's one of our earliest ways, but it's difficult to use these historical photos to quantify the volume of material that has been lost from a glacier, namely the volume or the material being the water. So I brought this up at the beginning of the presentation. Why do we observe? We're not just collecting things and collecting photographs to remember the legacy of glaciers on the landscape, but rather we are observing to improve theory and also to improve physically based models. A good analogy of this would be weather forecast models. Those forecast models have dramatically improved through time, both through improved physics, but also through increased observations of the atmosphere. And so that plane, for example, that I was showing you traveling from Europe to Vancouver, that plane, like many other planes, are constantly relaying their temperature, pressure, and atmospheric or elevation rather, to the World Meteorological Organizations, which then will take all of that data and improve physically based models through data assimilation. So in a similar way, that's what we do with glaciology. We make observations to improve these models. Okay, most of what I'm going to talk about for the remainder of the talk really has to do with remote sensing. So the way that we can observe glaciers both from aircraft, but also from spaceborne observations. And so in order to do that, we have to think a little bit about the type of energy that we're sensing and whether these sensors are active or passive. If we were to observe optical properties of Earth's glaciers from spaceborne observations, we typically exploit the reflectivity of those surfaces and sunlight and how sunlight interacts with those surfaces. The nice thing about glaciers and snow-covered terrain is that it is highly reflective in the shorter portions of the visible portion of the spectrum. So that portion that we can actually see with our eyes. Another advantage is that when we get out to the longer wavelengths, the shortwave infrared, snow gets optically dark. And so we can use that difference to effectively map out where glaciers exist. We can also use active remote sensing, such as light detection and ranging. So this is laser light, both in the shortwave infrared, but also in the visible portion of the spectrum. So this green and red box represents LiDAR systems. I'll talk about the LiDAR system that we have on an aircraft. And then these are examples of all the different types of sensors we have at our disposal, but also the different ranges over the corresponding wavelengths that can be used to understand the optical properties of snow and ice surfaces. So if you wanted to say something about glaciers and make observations of glaciers, you could do it over a variety of spatial and temporal scales. As I mentioned, I'm going to give you a couple of examples. I'll give you one from an airborne platform that we use, and I'll also talk about optical satellite systems and how we can use those to understand something about glacier change. I'm going to skip that one just to keep on time here. So one of the things that if you were going to take away from today's talk is that we used to be really limited by data availability. When I started doing this about 20 years ago, it took a lot of effort, took a whole team of scientists to compile and analyze Landsat data, so one of the earliest optical satellite platforms. It's now something that I could teach my 14-year-old how to do with very small amounts of code, and he could analyze hundreds of scenes overnight. So we have really reached a point where data availability and computing is no longer a limitation. It's one of the limitations is just creativity and trying to think about what to do and what to do that someone hasn't already thought about, like many disciplines. And so a couple examples I'm going to give you here, and I'm sorry that maybe this is kind of mean to show for Glenn, but most of you perhaps are in the UK and it's now dinner time, but maybe this is kind of mean to show Glenn a stack of pancakes. But think of the way we analyze satellite imagery, whether it's optical imagery or any other type, as rows and columns or pixels, and every scene ends up being another acquisition date. And so what the community is now starts to do is they start to look at what's called trend analysis. So for any location on a satellite scene, a row or pixel, they can drill through that stack of data and start to analyze trends. Those trends could be surface optical properties. It could be elevation change. I'll give you an example of elevation change to illustrate my point here. But this whole idea of using one or two scenes to say something about what has gone on is almost become a bit passé with the amount of data that we have now at our disposal. And so with that, I'll give you an example of one of the studies that I was part of. This was led by a French PhD student who's now a postdoc at University of Washington. And what it looked at is using this stack of satellite data But in the case of Roman's study, it wasn't optical information, but it was rather elevation change. So he was using a type of sensor called the Aster sensor. NASA was produced by NASA, and it is still flying. It was started in 2000, my mistake. And this particular sensor acquires optical imagery, but in a very similar way as air photos are acquired. That is, the satellite acquires a scene directly below it. 20 seconds later, it has another camera that shoots backwards, and it produces a stereo pair. And by using principles of parallax, that things closer to the sensor shift more, you can actually produce a digital elevation model. And so Roman was able to take hundreds of thousands of these stereo pairs and examine elevation change for all of our glaciers. So just to give you an example, this is this upper left. This is the stereo scene that Aster would acquire. So again, it's got a camera or a sensor that acquires a scene directly below it. It flies 20 seconds later or so, and actually 64, and then basically takes another backwards looking, and then it actually has a stereo pair. And if you do that, and you do that for the last 20 years, you can get on average something like 8 to 9 individual stereo pair scenes for a given glacier for all of Earth's surface. And so these all needed to get processed. So working with Roman, we used a high performance computer here at UNBC and ran it for one entire year. I didn't feel as guilty as other places because we're hydropower. So it would have been a lot of energy consumption in a place for fossil fuel use. But this kind of allowed us to do the computation that was needed to do. And what we can then do, and what Roman did, is he then took 2 10-year time periods and averaged to examine how those glaciers are undergoing elevation change through time. So you can envision this as taking the average for the first decade and the second decade and differencing it. And in addition to that, we looked at climate data that's produced on a grid, and we wanted to understand the climatic drivers, that is, a change in temperature or a change in precipitation between those 2 decades. And what you can see as this animated GIF goes through is you can see that, for example, in Western Canada, the difference between those 2 decades, the glacier melt accelerated, and it was not only conditioned by an increase in the temperature, but also a drying trend. And you can start to see that in other places. If we got a little bit closer to the UK, for example, we can start to see some different patterns, different variations. By and large, though, glacier melt on the planet has accelerated in those 2 decades, and it is consistent with what we would expect based on the temperature and precipitation forcing. Okay, I'll give you one more example, and that is from an aircraft. So often, if we want to say something about the entire planet and how mountain glaciers respond, we have to actually consider spaceborne observations. But there are times where we wish to say something with greater frequency, or we wish to use both sensors that can tell us something about elevation change, but also perhaps surface optical properties. And in this case, it's really through an amazing partnership with a nonprofit organization called the Hackeye Institute. I've had the luxury of working with the Hackeye Institute to better understand how glaciers in the landscape in Western Canada are changing. So we lease an aircraft, which we call the Airborne Coastal Observatory. And this, again, is a joint partnership between Hackeye and the University of Northern BC. So this particular aircraft is used to not only understand glaciers and how they respond, but also how nearshore habitats or watersheds are responding to climate change, or how they're undergoing dynamic change and will undergo those changes in the years ahead. We use this particular platform for geohazards, so times where we actually might get a landslide. We've been asked by many organizations to help do some mapping for them. So BC Parks is an example where we helped following a flood from a couple of years ago. And so this particular aircraft, it's a twin engine. It's a Piper Navajo. This actually has a operator that, in addition to the pilot that sits, of course, up front, the operator sits behind. We have airphoto cameras. We have what's called a laser scanner. So this is a LiDAR system with a very precise GPS, much more precise than what we may have in our phones. And then we also have what's called an imaging spectrometer. So this allows us to image below the aircraft in hundreds of channels, discrete channels, and the visible and near infrared portions of the EM spectrum. So I'll give you a couple of examples here. Here's the typical flights that we fly with the ACO. I'll show you an example of my favorite glacier, Clean. This is also the one that I believe Glenn had on the handout to announce the presentation today. So that was taken from the ground, but I'll show you what Clean looks like from the air. These are typical areas that we fly once or twice a year. And in some cases, we fly one particular glacier about 10 times a year. And the reason we do that is to come up with monthly estimates of melt that we can use to calibrate physically based models of glacier mass balance. So in order to do the work we do with this aircraft, we have to actually go through a whole host of different steps. We have to plan a particular flight. We have to post-process the lines once we actually acquire the data. Then we proceed with what's called co-registration. So even though we have a precise GPS, we have to ensure that all of the surveys, if we're doing a repeat survey, are precisely co-located. And that's simply because if you're off by a little and you're in really steep mountainous terrain, that is, if your horizontal offset is a little too much, then you can actually get a lot of vertical change, which is not real. It's just simply because the elevation models are misaligned. So you have to actually ensure that those are aligned. Once you do that, though, you can make maps such as this. So this is Clean Glacier and how the elevation has changed over the 2018 to 2022 period. To give you an idea, so this scale bar, this is about 1,000 square kilometers. So this is one of the largest glaciers that we have in Western Canada. This ice glacier complex loses about a gigaton of mass, or a gigaton of water per year. To give you so a gigaton is a cubic kilometer of water. It's a lot. It's really hard to sort of envision. I think a typical pickup truck is it's a long bed could hold about a cubic meter. So I guess we're talking about 1 billion pickup trucks worth of water. So it's a lot of water that we're talking about here. Most of the glacier's thinning. Most of the ice field is thinning. We do have some thickening, but by and large, that is well compensated by the strong mass loss that we're experiencing over that glacier. One thing you can also do with these data, just sort of cycle through a little bit. If you keep your eye here, you see that this hillshade and the two different time periods, this whole hillside is moving. So as this glacier is thinning and melting away, the hillside is starting to destabilize. So we're also looking at how these landscapes are undergoing change due to landslides, simply due to the removing of this buttressing or supporting ice. So this is an important thing that we try to consider when we're looking at these deglaciating landscapes, is the geohazards that can occur from these environments. One thing we also can do, this is an example of an ice field that is seen on the Bridge Glacier. So this is near anyone who's been near Vancouver or Whistler, BC. This is about 100 kilometers away. This is a hill-shaded image. The white areas here, these are just missing data, but this is about a month separation. And you can see that in addition to seeing the crevasses, you can also see that they're actually moving. And so what you can do is you can actually use these data to map how fast the glacier is flowing, the surface velocity. So this just shows between that roughly month time period, what the velocity is in terms of meters per year. Not surprising, the fastest flow, the one I just showed you, was about right, actually it was right here. Here's Bridge Glacier. And you can see that the fastest flow tends to be in the middle part of these glaciers and away from the edges, largely supporting what we would model from a theoretical standpoint. Okay, one final example of what else we can do with these, with the aircraft. So this is my former student, Ben Pelto, engaging in some routine glaciological work on several glaciers in the interior of BC. It's laborious, time challenging. It's also fun work, but to get to all of the glaciers in BC, we could never do it. We have something like 16,000 individual glaciers. So these are about 5 different glaciers that Ben was working on. And it took him way too much time, simply because trying to visit all of these glaciers, measure the amount of mass accumulated and the amount of mass lost each year is quite time consuming. It's also subject to notable hazards. So it's hazardous terrain with crevasses, snow avalanches. And this just gives an example of one particular glacier, looking at the different locations where Ben and his team would go and measure the amount of water that was gained or lost each year. This is this is a plot that just shows the relation between those different glaciers that Ben worked on and what he measured in terms of glaciological mass balance, and what we could do with Ben using an aircraft and making very simple assumptions on the density of what the snow and ice was. And you can see that the correspondence is quite good. So this allows us to not only say something about the glaciers he worked on, but also to estimate the mass balance or the amount of water gained or lost for hundreds of different glaciers that we routinely fly each year. Okay, and my final example, if I'm doing okay on time, is I will just briefly introduce some of the more recent work we're doing with this aircraft, and that is to say something about the surface optical properties. So one of the sensors we have aboard is this hyperspectral sensor, and we can say something about impurities that may be deposited on these snow and ice surfaces. This is an example of this is seen from MODIS, a spaceborne image in summer of 2017. And Glenn probably remembers this. This was a bad wildfire year. We had lots of wildfires to the west of Prince George. But in addition to really bad air quality in and around Prince George, you can see that this smoke also starts to drape and cover the ice-covered areas in the interior and Rocky Mountains. And so the reason that's important is that those impurities, primarily soot and ash, will tend to darken those surfaces. And so if we darken those surfaces, even if we don't change the surface air temperature, we can have a dramatic effect on how quickly these glaciers are melting. And so most of the current models for how glaciers are expected to fare only look at the thermal change under greenhouse gas emissions. No one's really considering things such as surface darkening and how that's likely to change. So unfortunately, I'm going to hypothesize that we're going to see a much more rapid melt in the decades ahead, unfortunately, due to wildfires. So here's an example of what late ice looks like. This is near Yoho Jasper, so in the Rocky Mountains. This particular surface was inundated by wildfire. There's also natural debris that starts to emerge on the glacier, but this is quite a dirty surface and will absorb much more energy from sunlight than the little bit of retained snow that this sort of surface would collect. And so if you looked at these, the wavelength and the reflectance, here it's written as spectral albedo, just take that as being essentially reflectance for our discussion right now. But you can see if we start to add impurities, or if we start to change the grain size of the snow, we can have a dramatic effect on how reflective those surfaces are. And in addition, if we start to add snow algae, this blue-green algae that it has a lot of red pigments, that too can actually start to affect how these surfaces are reflective. And so this is something that we're currently working on, is trying to understand how the reflective properties are influencing melt for these glaciers in Western Canada. So this is one of my current master's students, Charlie. We were out on a glacier last summer, and she's got what's called a field spectrometer. So this is imaging light in both the visible and near infrared in hundreds of channels. That's what these traces are on the right. And you can see this red, it almost looks like a murder scene. It's not, it is just snow algae. So Charlie is measuring the difference in reflection between this surface here and the corresponding brighter surfaces. And when you look at the snow algae plots, you can see this absorption feature. So she can actually start to look at how important that is for this particular glacier. And so we're trying to also do this not just for one glacier, but a whole different host of glaciers. That requires a similar workflow to what I showed you for the digital elevation models. We have to take raw data. We have to consider the atmosphere and how the atmosphere may influence that light reflection. And then at the end of this workflow, we can get out products such as albedo, which is the proportion of reflected to incoming light. We can also come up with grain size and this term radiative forcing. So essentially say how much energy is being absorbed by that surface due to things like impurities or due to changes in grain size. And those impurities, again, can come from things like wildfire smoke. They can also come from dust and other phenomena. But by and large, in Western Canada, we're seeing a profound increase in the darkening, we think, due to wildfire smoke. And so if you were to look at some of those features and some of those products here, just to give you an example of some different days, you can start to see as we move through the melt season, this is a typical RGB, so red, green, blue image. So this might look similar to what our eyes see, but then we can actually start to see these individual products such as albedo or optical grain diameter, or in this case, radiative forcing. So how much energy is being absorbed of that surface per second per square meter. Okay, so I'll leave it there. I was hoping to be done 5 minutes earlier, but just suffice it to say, and I'll reiterate this point, data availability and processing no longer seems to be an issue. It's rather trying to find time and talented students to actually work with. I didn't say this at the beginning, but I will say that any slides that I have and have shown that you may wish to use as part of teaching students, by all means, I'm happy to share those if that helps in any way. Because I do think the older I get, the more I realize it's not going to be white-haired guys like me that convince. It's really going to be about students that are sort of talking to teachers such as yourself and saying, okay, I want to go into that career, or I want to do something about changing the planet. So thank you very much.
Great. Thank you so much, Brian. Besides the insight into the science of glacier change, this talk was also an important reminder of the value of disciplinary knowledge, of the historical record, which can take many forms, and indeed the interdisciplinary nature of the study of climate history. One of my immediate takeaways is that it feels good to trust the science when the science has been explained in a way that I can understand with relevant examples and carefully reviewed evidence. It's this kind of confidence in the reality of climate change that is foundational in our work with students. So let's open it up for questions. We have about 9 minutes for that, and then we'll wrap up at that point at 1:30. If you did want to stick around for another few minutes after that to hear from the Teach Climate History Steering Committee about our plans for the coming year, that's an option as well. Allison did have to leave, and she's kind of our ringleader, so that might be a short extension. So feel free to open up your microphones, and if you've got a question to ask, that would be great. There was a question from Hart Bannock just before he had to go, and that was, what are the messages that you would like to communicate, Brian, to K-12 students about the work and the science of glacier change? And are there impacts of this type of research for classrooms and teachers?
Yeah. So I think that, the times that I've talked to high school students, what really makes me excited these days is not necessarily writing yet another paper, but rather having a high school student or an elementary school student come up to me and say, that's really interesting. Can you do a career in this? Not necessarily being a professor, but rather remote sensing and geospatial technologies. I can't keep students. That is, they are constantly sought after by industry, and it's not just me, it's anyone doing remotely sensed observations, to Earth observations. If you like technology, it's a great place to think about a career. We often think about and talk to students, and I'm always wondering, why aren't students more interested in Earth observations? They want to go into banking, they want to go into finance, and is that simply because that's what society has as examples? I think for myself, the most important formative events of my own education were good high school teachers, and that influenced what I do, certainly. And so I think when you can get the point across as a instructor for students, that's absolutely essential.
Any other questions for Brian? Tom, go ahead. You're muted, right, Tom? Here we go.
I have a quick question about the Indigenous perspective on glaciers, the idea of them as being sentient, and that the anthropologist Julie Cruikshank asked us in general to listen to glaciers, and I'm just wondering if you want to comment. I mean, there's a huge gap between your presentation and the scientific and this kind of concept, but where do you see they might connect together? What might be their overlap?
Yeah, that's a great point. And Julie's partner actually was one of my mentors, Gary Clark, and so I know Julie quite well. I think in many ways, when I first started as a scientist, the Indigenous perspective really, it was certainly considered, but it certainly was not common. And recently, I had the honor to actually work with First Nations chief from the Hamalco First Nations, We did some work on their territory, looking at a landslide, but also glaciers. And I reached out to the chief and made him a co-author on one of our scientific papers. I wondered whether I would get some flack from the academic journal, because they often have certain standards on what's required for authorship. But I was also ready to defend that this particular individual invited me to their territory. I'm observing, so they were actually part of the science. I think that's, I don't know how frequent that's going to be the case. That is, I often talk to First Nation communities along the coast about glaciers, but clearly they have also other pressing issues. And so I think part of it is trying to balance what is important for their own societies and listening to what they wish to hear. But certainly I'm more than willing to work with whichever First Nation actually has questions.
What I was interested in, I think that's interests me very much, what you just talked about, but I was also interested in how their perspective of glaciers as being living relates to what you do, and where there might be some connections.
I've often asked certain communities for if they know if they have names for particular glaciers. They anecdotally have said that these glaciers are changing quite profoundly and rapidly. So there's no question there's overlap there. I feel sort of, I don't have the tool set to fully engage and interact in a way that perhaps would be as important and meaningful as perhaps someone else would. But I certainly would welcome to learn how to better incorporate that knowledge into the sort of information that we do.
Thank you.
We've got about 3 minutes left, and we've got two questions to pick from. One is, do you think climate scientists have a duty to be activists on climate? Scientists are widely respected, and scientists participating in activism and protests sends a powerful message. And then the last question was, how far is your current research percolating into school curriculum, the scope for students to being involved in the monitoring and so on? So either one of those, maybe?
I could say quickly, I think it's absolutely essential to report out on the science. And I think the term activism has been a misguided concept. That is, if it is a doctor an activist, that they say stop smoking because it causes cancer. I don't think so. They're just telling you their point of view as an expert. So I routinely talk to the media at every opportunity. I say we must reduce greenhouse gases. That's not being an activist. That's just being a scientist. So, sorry. School curriculum. Yes. I very much am happy to share and have always shared my information with different communities for schools. I haven't been approached by like the BC government to sort of incorporate stuff, but I know that we've contributed to some of government's information, and I don't know how much gets in there. I do have an idea, but I haven't, I should do this. I'm on sabbatical. I want to write a kid's book, a graphic novel about glaciers from a 12-year-old's perspective, a girl who lives somewhere in the Central Coast. And she goes to NASA down to work with NASA and learns about glaciers because her crazy, her nerdy aunt is a good scientist down there. So now I've told someone, so now I have to actually make sure that I do it someday. So.
Right. And thank you, Barbara, for your comment about Helen Caldecott. And yes, please, on the graphic novel. So that's about all the time we have today. We really appreciate taking the time. Afternoon, a twilight session, I believe, as they call it in the UK. I love that term. And for us on the west coast of BC, it's time to clean up the breakfast dishes and get back to the rest of our day. So thank you so much for joining. Appreciate your time. And thank you again, Brian, for your talk. Wonderful.
Thank you very much.
Yeah.
Have a good evening.
Great. Yeah, thanks.
Okay. Bye-bye.
Bye. So I'm not sure between Tom and Michael or anyone else from our steering committee that wanted to say anything. Allison's had to leave, but if anyone else wanted to throw a few words out, now would be the time.
Thank you. Well, first of all, thank you for organising this, Glenn, because it was fascinating talk, really. And yeah, and thanks for introducing it so well. Really, really great, I thought. Well, Alex and Gary and Bob are still here. Neb's still here. We as I say, this is the last kind of talk in this academic year, but the group will be meeting in July to plan next year. And we have some ideas of who to invite, but it'd be really good if you can spare just 5 minutes now, just your views. That can be kind of general, because one of the discussions we've had is, do we want to keep this balance of, okay, so we've had a scientist. Last time we had a primary geographer speaking to us. Historians, this balance of academics, but also educationalists. So